In today's lecture, we're going to start talking about bosons, so the other type of quantum particle compared to fermions. And specifically, we're going to focus on building up the formalism to describe massless bosons. And then partway through the lecture, we'll specialize to photons, those particles of light, talk more in depth about them. But at the beginning, we want to start a little more generally just because there are other types of massless bosons. In particular, we'll talk about phonons, which are particles of sound, and magnons, which are sort of particles, not really particles, quasi-particles of magnetic excitation. So photons aren't the whole story, but they are the biggest part of the story, and that's why we'll specialize to them partway through the lecture. For concreteness, we will actually start talking about light and then step back to take a little more general formalism. So the picture that you want to start with for thinking about the thermodynamics of light, well, if I turn on a flashlight and some light goes shining away from me, there's no sense in which that's going to be at equilibrium, right? It's traveling away. I need my light to be sort of trapped in one spot. Then I can think about light coming to equilibrium. The way we'll talk about trapping light in one spot is in some kind of cavity. So literally just a container with an empty spot in the middle. And in the middle where there's no material, we can have light build up an equilibrium state. So let's start in 1D. Cavity in 1D is just two mirrors. Okay, so light can bounce back and forth. And when I say light here, what you should really be hearing is electromagnetic radiation. So it doesn't have to be in the incredibly narrow band that we can actually see with our eyes. Okay, it could be radio waves, microwaves, infrared, ultraviolet, sort of any part of the electromagnetic spectrum. And in fact, we're going to do integrals over frequency that cover the entire electromagnetic spectrum. Okay. But that's a mouthful, so I will be saying light. Okay. So what happens if we have a cavity? We've got two mirrors, and at the mirror, the electric field had better go to 0. All right. So we've got a boundary condition that tells us what kind of standing waves, right, can fit inside of this cavity. And these may be looking very reminiscent to when we did the 1D particle in a box. Okay. Now, when we have these things in a cavity, if I look at a single mode, right, let's say just this, the white ground mode, okay, this is the longest wavelength mode that fits into the cavity. If I ask how much energy is in that one mode, rather than in the entire cavity, but just in that one mode, how much energy is there? Well, you know, or hopefully you've seen in E&M, that the energy density of an electromagnetic field is proportional to the electric field squared with the permittivity, plus the magnetic field squared with the permeability. That's the energy density, and a mode fills a certain volume, so the total energy is also going to be proportional to this, as well as the volume. Okay. So, well, we've got something whose energy is the sum of the squares of two different things. Okay, call them p squared and x squared. Okay, mathematically, it looks the same as a harmonic oscillator, right? Which I've said in words. Each mode looks like a simple harmonic oscillator. Now, based on that and what we already know from equipartition, right, that's 2 degrees of freedom, we can say, yeah, the heat capacity is going to look like N times K, right? So we get 1 Boltzmann constant worth of heat capacity, or said differently, at a certain temperature, we'd have KT worth of energy per mode, and then we have N modes, so we multiply it out. Great, this should be easy. There's just one problem. If we start looking at the modes in this cavity, right, anything whose wavelength obeys this form, right, 2L over some integer, is a valid mode. So if I want to multiply Boltzmann's constant times K to get the heat capacity, well, okay, how many modes are there? Lambda n is 2L over n for any integer n, there are a lot of integers. There's an infinite number. Okay, so that would be a problem. N would be infinite, which would mean the heat capacity was infinite. At non-zero temperature, the energy content would be infinite. This would be very bad. Okay. And people were aware of this problem in the late 19th century. And the way they described it is the ultraviolet catastrophe. Okay. So as the frequency goes higher and higher, you never run out of modes. And so if you just naively take classical statistical mechanics and try to apply it to electromagnetic fields, you get this infinite result. That has to be wrong. Okay. Luckily, we know the world isn't just a classical harmonic oscillator. It's a quantum harmonic oscillator, maybe. So what about the quantum harmonic oscillator? Well, way back in problem set 1, you calculated some things about it, right? Like the partition function. Some of you may have horrible memories of this. Hopefully not. So the partition function for the harmonic oscillator looks like so. And if we calculate the average energy, so remember, again, we're saying a single mode of the field looks like a quantum harmonic oscillator. So this would be like the partition function for a single mode. What's the average energy in a single mode? Again, something that you've worked on in previous problem sets. Minus 1 over z, dz d beta. Okay, hopefully that sounds familiar. This is your average energy. And just churn through the derivatives, we get hf, right? So Planck's constant times the frequency over e to the beta hf minus 1. And okay, so that gives us an energy. One thing that looks good about this is if we start doing a sum over the modes, right? Before we said, well, we just got kT per mode times n, and n is infinite. Okay. Now we don't have kT per mode. We have some more complicated relationship with modes. And what that tells us is that when we do the sum over modes, it's going to look more like, an integral over f, or at least a sum over discrete frequencies. And we've got an exponential in the denominator. So we have an infinite number of modes because n, that integer, can go higher and higher and higher, which means the frequency can go higher and higher and higher. But the actual average energy we find per mode will be suppressed by this exponential factor. So this looks like it's going to solve our problems, and in fact we'll calculate soon that it does solve our problems with trying to describe light in a statistical mechanical fashion. Okay, good. So we've got a promising lead here. One last question we might ask, because it's what we've asked with fermions and with quantum particles in general, is what's the occupation of the mode, right? So a mode of the electromagnetic field is going to be analogous to an eigenstate of a material particle. Okay, there are subtle differences that at some point in your career you may get into, but for the moment we'll say if we've got a cavity and there are modes that fit into it, that's sort of directly analogous to the levels or the eigenstates of a material particle. Great, so what's the occupation of the mode? Well, we know the average energy, we got that, and any excitation of the mode has exactly hf of energy, so the average occupation of the mode is just going to be the average energy over hf, 1 over e to the beta hf minus 1, which is exactly the form of a Bose-Einstein distribution if you set mu equal to 0, right? So hf is the energy of the mode or the state or the level, right? So we've got e to the beta epsilon minus 1. Great, so it's a Bose-Einstein distribution with mu equal to 0. So this thing looks like a Bose-Einstein distribution, and we know that that should give us the occupation of a certain level, which is to say the average number of particles in that level. So we're now going to be thinking about excitations of a mode as particles, and the name that we give them is photons. Okay, you've probably heard this term before. Photon is a particle of light, And the clearest way to understand is, in fact, in the context of a cavity. So if you've got light trapped, then an excitation of a mode is a photon. Now, since we're talking about light, and light moves, shockingly, at the speed of light, you know from relativity that means that if a photon is a particle, it's a particle with zero mass. Okay, that's the only way something could move at the speed of light. M equals 0. The fact that m equals 0 is going to lead us to this conclusion that the chemical potential is 0. And the story, Schroeder gives a nice sort of two different explanations for this. I'm going to give you the one that I liked better of the two because it's a bit more general. Because it's a massless particle, they can be created or destroyed. Sort of, if I have a cavity at a certain temperature, I can't tell you to begin with, hey, what's the number of photons you have trapped in there? Because as I change the temperature, the number will change. Okay, so this is a very different scenario to, say, a gas trapped in a box, where I know how many atoms are in there. I may not know how fast they're moving, that sort of thing, but I know how many atoms are in there because atoms can't just be created or destroyed at normal temperatures. Okay. For a mass equals 0 particle, at any temperature, some particles can be created or destroyed. And because of that, if I look at the Helmholtz free energy, right, the equilibrium state of the system will be the state that minimizes the Helmholtz free energy. And in particular, because the number isn't fixed, the number of photons in the cavity will adjust until you reach the minimum of the free energy. That is to say, if it's the minimum as a function of number, the derivative of the free energy with respect to number is equal to 0. But that's exactly the definition of the chemical potential, and so the chemical potential must also equal 0. Okay. So again, this idea that the chemical potential for light is 0 is coming from the fact that there's no minimum cost to make a photon, right? You can just make the frequency lower and lower until you get to the ground state of the cavity, but generically, when we're looking at cavities, the ground state is so low in energy compared to kT that that's sort of not a concern. So massless particles lead you to 0 chemical potential, and that's exactly what we found sort of from the opposite direction. One last thing I want to say before we move on, the idea of quantizing the harmonic oscillator so that you have, a specific energy for one excitation, and then you can count how many excitations you have. This is, in some sense, historically how Planck started the whole quantum revolution. And the way he described this was as an act of desperation. So I mentioned this UV catastrophe. This was one of the most vexing problems in physics at the end of the 19th century. People had worked on it and just got nowhere. So this was, some people might say, Planck's flash of genius, because in physics we like to talk about things this way. But really, it was an act of desperation, his own words. Now we want to take our understanding of individual modes, put it together into calculations of the total energy of the system. So we've got our mode has some wavelength, and depending on what n is, we're going to have an energy which is Planck's constant times the frequency with n. Frequency for an electromagnetic wave is just speed of light over the wavelength. So the wavelength is now in the formula, and we saw before the wavelengths that fit into our 1D cavity have the form 2L over n. Okay. So the nth energy is hcn over 2L. And this is similar to the 1D particle in a box, except that this is linear in n rather than quadratic in n. And of course, there's no mass in the bottom like there was for the particle in the box because we have a massless particle. Okay, so this is our energy. Another way to think about this is that the energy for a massless particle is just the momentum times the speed of light. Momentum, we know from de Broglie's relation, is Planck's constant over lambda, over the wavelength, and c over lambda, right? So this, we've gotten back to the same formula again, and now we're going to do the same thing, which is plug in the values for lambda and get our energy formula. Either way is nice. Thinking about it in terms of momentum, though, helps you to understand what should we do when we go to more than one dimension, right? In 1D, it's just n. There's only one n. That's fine. In 3D, the momentum, right, the thing that gives you energy for a massless particle is the magnitude of the momentum, which you get by just taking square root of the sum of the squares of the components, right? Just the length of the momentum vector. When we have three-dimensional cavity, right, we'll have, modes in the x direction, the y direction, the z direction, and we could have a mode that points in some other direction. What will control the energy, in other words, what replaces the n up here, is just the length of this vector in n space. Okay, so you can think of n space the same way that we did when we talked about fermions in a box, right? It's just nx, ny, nz, nz. I'm losing my z's here. Right, you've got three-dimensional space. States are represented as the points on the corners of a grid, right? So integer coordinates, and it's going to be 1/8 of a sphere in the case of 3 dimensions. And because the relevant quantity is the length of that n vector, when we want to describe this, we're going to go to spherical coordinates again. So I think a number of you had a tough time thinking about the coordinate system for a 2D harmonic oscillator because it wasn't sort of one of your standard spherical, polar, cylindrical that you may use pretty often in courses. It was in fact just a rotated Cartesian coordinate system. But so for photons or for any massless boson, the momentum is going to be related to the length of the n vector. Okay, good. So that's how we're going to think about this in n space. And so our formula for energy just pulls directly down because I've named the length of the n vector as little n. Okay. Good, so there's our energy. So now, before we go and do a calculation, and yeah, you can see down here there's some integrals, there's some stuff going on. Don't look there yet. This is actually a good general rule in physics. Before you embark on a calculation that looks like that, ask yourself, what answer should I get? Okay. See if you can sort of deploy some physical intuition to know the form you expect in the end. And this is having physical intuition is in some sense why we're here, but also if you think about how things should look, then you can mechanically grind through the calculation at the end, see, did I make a mistake? Okay. Now, we can't check everything quite like that. You do have to be careful when you do calculations, but okay, so what should you look like? What should the total energy of a gas, for lack of a better term, right? A gas of photons inside of a cavity in 3D. Okay. Well, one thing that we suspect is that if I take the average energy per particle, right? So U is the average energy of the system. Take the average energy per particle. I expect that that's going to scale with the temperature, right? That's certainly what happened for our massive particles. And in some sense that shouldn't be surprising, right? We think about Boltzmann factors. The probability of a state comes from the ratio of its energy to kT. So just generically, we should expect that per particle, our energy is going to scale with kT. Okay, great. So if we know the per particle energy should scale with kT, how does the number look like? And the one thing that I know is for a given cavity, if I make it twice as big, right, what have I done? Well, if I look up here, I've made L smaller. Sorry, I've made L bigger, which makes the prefactor on N smaller. So for a given KT, I've got twice as many modes available. Well, that's generically true. If I change the volume, the number of particles at a given temperature will be proportional to that volume. Okay? Or to say it differently, in the case of photons, number is an extensive quantity. You know generically energy is an extensive quantity. And in the case of photons, again, because they can be created or destroyed, the number will also be extensive. Good, so E bar over N proportional to KT, N proportional to V, put it together. We expect that the energy of the system is going to be proportional to KT times V, but now look, that doesn't have the right units. KT has units of energy, but we've got a volume sitting there. So we want some length scale that we can use to cancel out the volume, right? We want to get this the right units. Okay, so what's a characteristic length scale for this problem? I can think of two. One is the size of the cavity. But we've already covered that. That's in V. V is exactly the size of the cavity. The only other length scale is the wavelength of the light. And so if this is going to depend on a wavelength, it's probably going to depend on the most probable wavelength or something like that. And we said if the average energy per particle looks like KT, then our wavelength, which is speed of light over the frequency, we can write it in terms of an energy, right? So frequency is just energy over Planck's constant. And then we can say, well, we think this should be proportional to KT. So great, let's just put KT in for the energy. H flips to the top, HC over KT. You can check the dimensions. This is a length scale. This is the wavelength for some kind of average wavelength in the photons. Right? So if this is our length scale, plug that into this, we're going to say, and why did I just realized, I hope this wasn't behind my head while I was talking about that. Wavelength is C over F, F is E over H, E per photon looks like KT, so plug in KT here, and there you go. Okay, so that's our length scale. And for some reason I went from average energy to U. They're the same thing, right? We're talking about the average energy of the whole system. Good. So U is going to look like some number times KT times V divided by this length scale cubed. So when I flip this, KT comes on top, I get KT to the fourth, V over HC squared. So I'm going to do a bunch of work to figure out what this number is. And I'm going to have a pretty good idea that I've done it correctly when all of the functional dependence, right? All the physics looks right. And then I'm going to get whatever, 75 pi over E times the Euler-Mascherani constant. What that number is important, but it's the scalings with physical quantities are what we're more interested in. So I need this number to be able to go do useful things in the world, so it's important. But if I know the scalings, I have a pretty good idea of the physics already. Okay. Great. So now let's go find the number. After I just denigrated this poor number, let's go find the number. So what do we need to do? We need to sum over the modes. And exactly like we did when we had a gas in a box, I'm going to take a sum over this discrete n space. Going to turn it into an integral because we're looking at a huge number of particles. And the difference between the sum and the integral is going to be minuscule on that scale. Okay. And I already hinted to you up above, because the energy depends on the length of this n vector, we can switch to spherical coordinates because our level curves, our curves of constant energy, are going to be spheres. Right? Good. So I keep saying photons or massless bosons. I'm saying them both. Now I'm going to nail it down that we're talking about any massless boson by putting a G here. Okay. So just like for fermion gas in a box, we had this degeneracy factor. Right? Is the electron, it's a spin half particle, so it could be up or down, degeneracy factor of 2. When we talk about a gas of nucleons, they could be either a neutron or a proton. either spin up or spin down, so G is 4. For photons, G is also 2. And if you have heard someone say something like, a photon is a spin 1 particle, you might be surprised that G is 2. Shouldn't it be 3? Turns out that when you're massless, essentially you lose a degree of freedom to the fact that you always move at the speed of light. So a photon only has a degeneracy factor of 2, and you can think of that as its 2 polarization states. Right? So if light is traveling directly toward you, it can't be polarized toward you either. Right? The field can't point in the direction it propagates. It's either polarized vertically or horizontally, or something that's a sum of the two. Okay, so if you've had optics, you can have circular polarization, elliptical polarization, but you can always project these out into vertical plus horizontal in some mixture. Okay, so G would be 2 for a photon. For a magnon, it'll be different. So for massless bosons, let's keep the degeneracy factor around. Okay, and now this looks almost identical to fermions in a box. Right? We switched to spherical coordinates. We've got our radial integral, got our azimuthal integral. We've got our polar integral and our azimuthal integral. And then the formula for the energy is the only difference. And a minus sign here because it's a boson. It's an important minus sign. Okay, so the two differences. The formula for the energy, which now depends on n rather than n squared, and they're bosons, so we have a minus instead of a plus. But the energy doesn't depend on phi, doesn't depend on theta. We can just do those two integrals and get a pi over 2. And then I'm going to change variables here. I want all of this mess that's up in the exponent to be my variable. So this looks almost like it. I just need to add a beta up top, so 1 over beta outside. And then, I've got 2 more n's and a dn, so I'm going to need 3 more copies of this normalization constant, right? And now I can turn this into an integral from 0 to infinity over x rather than n, so 0 to infinity dx. And I've got 2 n's here, a third n here. That turns into x cubed over e to the x minus 1. And now I just need to do this integral to get a number. But let me look out front first. I've got 4 betas, which is to say kt to the 4th on top. I've got L cubed, which is the volume. I'm going to pull that out, get a V. Okay, 2 cubed is 8, cancel the 2, find 4 pi g. All that's left is the hc cubed. So this has the form I expected. I've got 4 pi times g, and I've got the value of this integral, but this has exactly the functional form I expected. Okay, so in some sense, I say, great, this worked. Now this happens to be a pretty funny prefactor to get, and this as expected is referring to the functional form, not to the fact that this integral turns out to be pi to the 4th over 15. That's probably surprising, kind of like pi squared over the 6 from the last lecture. And in fact, you can find this in a similar fashion. We won't go through it. It's more that I want you to know these integrals can be done. And like I said in the last lecture, you can figure out how to do all of these yourself using essentially the same procedure we did before, just with more integration by parts. The one downer will be if this is an even power, you can't write this cool like pi raised to some power divided by some unexpected integer, right? You can't write the zeta function in that form, but you will get an answer in terms of a zeta function. And for zeta functions, just type it into Wolfram Alpha, what's zeta of 3? Okay, that's fine. Or just leave it as zeta of 3, and then your answer looks cool. It's got a zeta in it. Who doesn't like that? Okay, good. So here is our final answer for the energy. And just to clean it up a little bit more, I'll go ahead and put in G equals 2 for photons. So this is going to turn into an 8 pi, 4 more pi's, 8 pi to the 5th over 15, and exactly the functional dependence we expected. I've dropped the V over here because what I want you to see is when we have a gas of photons, right, or light in a cavity, either way you talk about it, there's an energy density, right, an energy per unit volume. That's really sort of the physical thing. The cavity gives you boundary conditions that allow you to do all these calculations, but sort of if you have an equilibrium system of photons, something is holding on to them, right? It could be that you're in a cavity that's like literally a box that holds photons. It could be that you're in a dense plasma so that the photons can't propagate away. You know, they're sort of interacting so many times with these ionized particles that the photons thermalize in that sense. Okay. There's actually another way that you can do this with dye particles, but so there's ways to have your photons thermalize. The point is, if you've got a thermal system of photons, energy per density is the right description. And so we have a pretty straightforward formula for the energy density. What's the interesting physics here? Probably the most interesting part, since it's the only thing here that's not a constant, is T, right? The energy density for your thermal system of photons depends on temperature to the fourth power. And that's it. That's the only dependence. Okay, pretty interesting. We'll come back. You'll see this T to the fourth appear again in a later lecture where it actually is important to like designing thermal systems, like building, maybe nuclear power plant, maybe air conditioning system. T to the fourth turns out to be important for keeping your computer chip cold inside your computer. Okay, so that we'll see again. Good. The other thing is I went straight to converting this into the nicest looking integral possible. If we were slightly less nice, instead of changing to x, I'm going to keep the beta in here, right? So I can change variables to energy. Okay. Now I've got an integral of this form. The only thing that's happened is the beta I threw outside isn't out there anymore. So I've got another form for the energy density. Some constants, integral, right? The energy integral looks almost identical except it's e to the beta epsilon. And this quantity that's being integrated, which is to say the constants that I pulled out front, if I pull them back in so that this is literally just written as an integral d epsilon, the quantity that I'm integrating here is the spectral density. Okay, and so spectral density is the energy density per unit energy, which sounds funny, but what I mean is per unit of photon energy. A better way to say it is, hey, I've got 3 E's here and I've got 3 H's here. Let's write this in terms of frequency. Okay. So the spectral density is the energy density per unit of frequency. Okay. And so this is something that we'll see a lot. This is the black body spectrum. Okay. You should definitely look in Schroeder. He has much nicer pictures of it than what I can draw. Look online. The black body spectrum is this really classic spectrum. So the idea is if I look in a certain window of frequencies, let's say I'm looking at 500 terahertz to 550 terahertz. Roughly speaking, that's what you see as green. Okay. I'm going to ask how much energy density is in the green for this system. I can get an answer to that. Now, if you have a box full of photons, you may not care how much green's in there because they're in a box. You can't see them, right? But that's why I said there are other ways that you can thermalize photons, one of which is if they're in a dense plasma. Our sun, great example of a dense plasma. So there is thermalization of the photons on their way out of the sun. And so if you take light from the sun and run it through a prism, okay, and then measure the brightness of the different spectral lines, okay, well, you'll see a continuum, not discrete spectral lines for the most part, and that continuum will have this shape as a function of frequency. So that's the black body spectrum. So one note before we move on to talk about entropy and number, I realized I said in the last section, this is the black body spectrum, but I never actually explained what a black body is. So when we talk about these photons inside of a cavity, the idea is that they're completely trapped in there so that there's sort of perfect interaction and everything is thermalized. If you had instead a thing that could radiate energy away, then it might or might not be at thermal equilibrium with the radiation that it's emitting. Right? If it's emitting it, the radiation's getting away. So a black body is, in fact, sort of literally a thing that looks black, which is to say it's a perfect absorber, but also a perfect emitter. So the spectrum that would be emitted by a black body at a particular temperature exactly matches what we've calculated here in terms of photons at thermal equilibrium. If you have something that's not a black body, then you can correct for that fact with something called the emissivity or the albedo. But basically, it's a correction that says this thing is not a perfect emitter or a perfect absorber, and so the power that it emits will be different, but the spectral shape will still be similar. One thing that we frequently want to calculate is the heat capacity of a system, right? We want to know how does its temperature respond to a certain influx of energy. Okay. So heat capacity, du dt, we've already calculated u as a function of t, so we can just do this derivative. Right, we had a t to the fourth, which is going to drop a 4 out front, where we had 8 pi to the fifth before. Okay, this is going to become kt cubed, and there's an extra k floating around now back here. But otherwise, this is just straightforward from the formula we had before. Okay. And now I've written a bunch of funny things around this in blue, which is when you look at this formula, it's maybe not immediately apparent that that has the right units to be a heat capacity. So I just wanted to quickly take a look. These are just numerical constants, so they have no dimensions. Kt is an energy, so we've got energy cubed. Hc, little funny, but Planck's constant is joule seconds, right, or energy times time. Speed of light is length over time, so the times cancel and you get energy times length for Hc, and the whole thing's cubed. Volume is a length cubed. And then I could have just skipped K in some sense because K has the right units, right? It's an energy per unit temperature. So it has the right units to be heat capacity. And then you can see, sure enough, the E cubes will cancel, the L cubes will cancel. You're left with K, which has the right dimension. Okay, so that's our heat capacity for thermal gas of photons. And again, I have now specialized the photons. The G is gone. I replaced it with a 2. That's how we got here. Great. So now I'd like to talk about the thing I said I'd talk about, entropy. And we're going to reach way back into things you learned last term in thermodynamics, namely that if I have an infinitesimal flow of heat, that is going to be the temperature at which the heat flows times the infinitesimal change of entropy, right? The entropy flow. And another way to say the heat is the heat capacity times the infinitesimal change in temperature, right? So heat is a flow of energy into the system. And if it's at constant volume, there's no work being done on the system. So the total energy flow is going to be the heat, which means the change in energy per unit temperature multiplied by dt. That gives us the heat. That gives us the heat. Let's forget about their name and just set them equal. Okay. If we solve for ds now, we're just bringing the t over, and I'm going to integrate both sides. The entropy I'm going to integrate starting from 0, which is the value of the entropy at 0 temperature, and I'm going to integrate it up to, well, s of t, whatever it is. This integral works if this side is integrating from 0 to t, right? So I'm integrating sort of along the same physical path, right? I start at 0 temperature and I warm up to T. And basically, as I integrate along that path, the entropy goes from 0 to whatever its value is at T. Okay, so this integral just gives me S of T. And this side gives me a whole mess of constants, which I pull out front, and then a T cubed, which needs to stay inside. So T cubed over T, this is going to give me a T prime squared. And now I just do the integral, right? This is going to become T cubed over 3, drop a 3 out here, bring the T cubed back. So our entropy, again, depends on this ratio, right? This gives us some length scale cubed or some equivalent volume that we can compare to the actual volume of the system, some numerical constants, and Boltzmann's constant. Okay. Good, so that's the entropy. I said entropy in number, and I said that because it turns out there's a nice relationship between them that we want to get to in the end. Okay, if I want to calculate the number, again, we can use some intuition like we did with U to basically figure out the form short of some numerical constant. Okay. So, and in fact, we already did the reasoning before, right? The number is proportional to the volume, but number is dimensionless and volume is not, so we need to divide by a length scale cubed to make it dimensionless. The length scale that makes sense is either the size of the system, which is already in here, or the wavelength of sort of an average photon, which is this guy. Okay. Good, so we're going to take this, put them together. The number should look like, well, the number of atoms should look like some number, some numerical constant, times kT over hc cubed times the volume. That implies, if we compare the functional forms, right, kT over hc cubed and a v, everything's going to cancel out except you'll get a ratio of numbers and you'll have one copy of Boltzmann's constant. That's it. So the entropy per particle is some number times Boltzmann's constant. We'd like to know the number because it turns out for some questions about the evolution of the early universe, the entropy per particle is an important quantity. So this is not just sort of an exercise in fun things that we can calculate, it's something that is useful out in the wider world. Okay, so n, we can go all the way back to the top when we were doing our integral to get u, right? Where did that come from? That came from thinking of states in n space, switching to polar coordinates or spherical coordinates, doing the angular integrals, right? March all the way through. I'm just going to grab the result that we had for u. What does this integral look like? No. The only difference when we calculate number is this stuff won't be here. Okay, we're just going to integrate over the mode occupation, not multiplying by the energy. So that's going to take away an hcn over 2l, which is to say we're only going to have x squared, not x cubed. That's it. Okay, so we come down and we end up with same 8 pi v kt over hc cubed. And now our integral to get the numerical factor has x squared instead of x cubed over e to the x minus 1. I told you before, continues to be true, you could in principle go do this integral yourself with the techniques we used last class. And in fact, even more profitable, you could prove a general relation, which is these things look like gamma of n plus 1 times zeta of n plus 1. Gamma of n plus 1 is n factorial, 2 factorial is 2, and zeta of n plus 1 is zeta of 3. There isn't a nice way to write this in terms of constants that you already know and love. And this value, 2 times zeta 3, is about 2.4. Okay. So our numerical constant out front is going to be 8 pi times 2.4, roughly speaking, or 16 pi zeta of 3. So that gives us our n. We still have our s up here. We can just take the ratio of the two, and what we find is, oh my gosh, so many numbers, Boltzmann's constant. You can do the arithmetic here. When the dust settles, we get 2 pi to the 4th over 45 times zeta of 3 times Boltzmann's constant. And evaluating this mess, we get, it's about 3.6 times Boltzmann's constant. Okay. So that is our entropy per particle for photons. Last thing I want to do before we close out is give you, I think, an interesting example of like, what do these numbers look like in everyday life? So I'm in a room, as you probably are as well. And in this room, there is some radiation field, right? Some black body radiation. Sorry, BBR here is my shorthand for black body radiation. Okay. And so the question is, what's the density of photons, right? Number of particles per unit volume at room temperature. And what's the total energy in the black body radiation in this room? Okay. So you've got all the information you need to do that. Pause, think it through, do a little calculation, and then come back and we'll finish it together. Okay, do you have a value? Let's run through it quickly. So the first thing we want to do is calculate this thing because it comes up in every formula. Okay. So KT over HC, just plug in the values. K, I'm using 295 Kelvin for room temperature because I've got Boltzmann's constant in Kelvin. Okay. EVs weren't going to help me out here. And Planck's constant, speed of light, just do the arithmetic. This is 2 times 10 to the 4 per meter. Okay. If I invert that, that gives me, again, a very rough idea of the kind of wavelengths that are near the peak of the Planck spectrum. It actually turns out, so when I invert this, I get lambda is about 50 microns. Turns out the peak of the Planck spectrum is, it's like a third of this, so 15 to 20 microns. Now, 15 to 20 microns is far into the infrared. Okay, so human vision is between 400 and 700 nanometers. If you've got a bright source, you can see 750, maybe even see 800 nanometers, but it starts to look just, the color doesn't change anymore, it just gets dimmer because your eye's not as sensitive. Anyway, all of those are shorter than 1 micron. This, again, this is 50. The actual peak of the spectrum will be 15 to 20 microns. So that's very far into the infrared. Okay, that makes sense. You don't see your room just glowing, right? Okay, so now that we've got KT over HC, we can run through the calculation. The number density, right? We have a formula for number up above, just bring the V over. 16 pi zeta of 3 times this stuff cubed. Okay. And I hinted at it before, I give it to you with a few extra digits. Zeta of 3 is 1.202. So we can plug that in along with the 16 pi, and our value for KT over HC cubed, there it is, 5 times 10 to the 14 per cubic meter. Okay. So in your room right now, every cubic meter of space contains 500 trillion photons, roughly speaking. Okay. It's a lot of photons. Good. Second question. What's the total energy in the room? Okay. So we know the energy density formula, 8 pi to the 5th over 15, KT to the 4 HC cubed. Bring the V over and plug in some numbers. Straightforward. Okay. We've still got the same KT over HC. We're going to cube that. We've got one more KT on top of that, right, to the 4th to the 3rd. So an extra KT and the volume of the room, roughly estimated. This is all rough. Even though I've given it to you to 3 decimal places, or 3 significant figures, yeah, this is not to 3 significant figures. I should have just been honest and called this 3 times 10 to the minus 4. But that's what we get. So the total energy in the black body radiation field in this room, 3 times 10 to the minus 4 joules. That is super tiny, right? What's a joule? It's the energy you need to raise something that's 100 grams by 1 meter. This is 10 to the minus 4 joules. So, it's the amount of energy you need to raise. Oh, there's a 3 out front. So something that's 3 grams by 1 millimeter, something like this. 30 grams. Raise something that's 30 grams by 1 millimeter. This is not a lot of energy. For comparison, though, I thought this was a bit of a fun comparison. A light bulb outputs about 10 watts of light, like one of your, these nice LED modern lights outputs about 10 watts of light, and the light travels in the room. I've got pretty light colored walls, so it's going to bounce once or twice before it's absorbed on average. So let's say the light travels about 10 meters before it's absorbed. Why do I need to know that? Well, because the power, right, it's joules per second. And I want to know, roughly speaking, how long am I integrating to know the sort of ambient energy in the light field in the room? 10 meters over the speed of light, I'm not integrating for very long, right? So multiply this out. The energy in the light field in this room due to a light bulb is like 3 times 10 to the minus 7 joules, even less. So the black body radiation, which you can't see because it's all concentrated at these long wavelengths deep into the infrared, it's got about 1,000 times more energy just sort of resident in the room than you have in the light bulb that you're actually seeing from. So hope that gives you sort of something to think about how much of the world we actually see with our eyes.